Hello everyone, I am ANIRUDH B S EE21B019 and my topic for the course EE5004 Seminar on the History of Electrical Engineering is the history of multicore processing and its need. Before we go on to understand what is a multicore processor and why do we need it today, we need to know what is a processor and its history and background. So, starting off, what is a processor? A processor is an integrated electronic circuit or a small chip that performs the calculations that run on a computer. A processor performs arithmetic, logical, input output, and other basic instructions that are passed from an operating system. Why was it needed? As evident from the definition, a processor was needed to perform arithmetic, logical, input-output operations at a much higher speed than humans could ever do. When was the first processor introduced? The first processor was introduced by Intel in 1971. Intel called it the Intel 4004 chip, which was a 4-bit processor. You can find the photo of an Intel 4004 processor here. Subsequently, in the year 1972, Intel launched its Intel 8008 processor, which was a 8-bit processor. The surprising thing to note about the Intel 8008 processor was that its pins were made of gold. You can find the Intel 8008 processor photo here. Moving forward, what are the types of processors? Processors can be broadly classified into two major categories. First being RISC-based processors and second being CISC-based processors. RISC stands for Reduced Instruction Set Computer, whereas CISC stands for Complex Instruction Set Computer. A number of systems going back to the 1960s have been credited as the first RISC architecture, partly because of the use of load and store approach. The term RISC was first coined by Dr. David Patterson of UC Berkeley for his RISC project. As stated earlier, RISC stands for Reduced Instruction Set Computer. RISC was a specific type of computer architecture designed to simplify the individual instructions given to a computer to accomplish tasks. The key operational concept of RISC is that each instruction can perform only one function. In CISC processors, it is possible that one instruction can perform more than one function. Another key conceptual difference between RISC and CISC is that RISC employs the load and store approach. That is, to perform any operation, you need to load both the operands from the main memory into the processor's memory before performing the operation. Whereas in CISC, you can perform the operation directly with both the operands sitting right there in the main memory. Today, almost all processors use RISC except the Intel 86, which uses CISC. Michael J. Flynn views that the first RISC system was the IBM 801 design, which began in 1975 and ended in 1980. As you can see from the pin diagram of a RISC and a CISC processor, the number of pins needed for a RISC processor is less than that of a CISC processor. Moving forward, the ever-increasing computer speeds and ever-diminishing circuit dimensions brought about by the technological explosion led to believing that the process would continue forever. However, was there a limit on chip size? It was observed that speed increased on reducing chip size. Moore's law stated that the number of transistors on a chip double every 2 years. It was an observation and projection of a historical trend that turned out to be an empirical observation-based law. Now, answering the earlier question, was there a limit on chip size? Yes, it turned out that there was a limit on chip size. This was first shown by Robert W. Keyes of the IBM Research Center. A study conducted by Robert Keyes of the IBM Research Center on limits in processor speed concluded that though the semiconductor or transistor size is going exponentially down, the voltage, current, and power dissipated on a chip essentially remains the same. He describes extremely beautifully in his paper Physical Problems and Limits in Computer Logic by Keyes in 1969 that the power dissipated in a chip having input impedance Z0 is essentially KT over Q squared by Z0. And KT over Q from our elementary semiconductor physics we know is the thermal voltage at any temperature T. Now this is the graph showing logic delay as a function of various years. This graph essentially shows that speed was increasing as years went by. This is Robert Keyes of the IBM Research Center. Moving forward, up to the start of the 21st century, single core processor performance was being improved upon due to the result of increasing transistor density on the die. However, as speed of the transistor increased, their power consumption also increased. Most of the power consumed by a transistor is dissipated as heat, which required increased capacity of cooling fans, and it was expensive. Now, the key question posed was, is it possible to increase speed without reducing size? This is the photo of an Intel fan which Intel uses as a cooling purpose fan for its chips. The question asked previously led to the emergence of multi-core processors. Multi-core processors emerged in the computing industry from uniprocessor technology as a method to achieve greater performance through parallelism rather than raw clock speed. Over the last 30 years, the computer industry developed faster and faster uniprocessors, though this pursuit is drawing to a close due to the limits of transistor scaling, power requirements, and heat dissipation. Because single-threaded cores are reaching a plateau of clock frequency, chip manufacturers have turned to multi-core processing to enhance performance using parallelism. Thus, the pursuit of a perfect uniprocessor stopped. This led to two diverse concepts emerging, the first being the multi-threaded processor and second being the multi-core processor. The multi-core processor differs from the multi-threaded processor, as a multi-core processor is a processor where the CPU cores coexist on a single processor chip, whereas a multi-threaded processor is a single CPU core that can execute multiple threads simultaneously. This graph on the right shows the performance gain as a function of time over various years. As evident from the graph, performance gain has only been increasing by increasing the number of cores on a chip. Next, Intel and AMD created their quad-core processors and launched it into the market. Here we can see two examples of multi-core processors. The first example being Tegra 3 processor, which had 5 cores. This was developed by NVIDIA. The second example is the Intel Nehalem processor, which had 4 cores and was developed by Intel. This is the Tegra 3 processor on the left, and this is the Intel Nehalem processor on the right. So, how did it all begin? It all began at IBM in 1996. In 1996, a handpicked team of some 250 system and chip designers, software architects, researchers, and semiconductor engineers set out to pull IBM of the last place in the fast-growing US 7 billion Unix server segment. They intended to leapfrog competitors such as Sun Microsystems, Digital Equipment Corporation, and HP with an entirely new system, one that would offer twice the performance at half the cost. To meet that lofty goal, they successfully put 2 high-performing microprocessor cores on a single silicon chip. At the same time, they developed an entirely new computer architecture, more of a new system than a chip. Their invention, they called it the Power 4, combined the best of commercial, scientific, and high performance computing in a single design. This led to the emergence of IBM Power 4. IBM Power 4. The first new system introduced with Power 4, an IBM E-server P series server called IBM Regatta, offered twice the performance at half the cost of its nearest competitor. Computing Business Magazine (EV) wrote, "The newly designed 1 GHz Power 4 represents a tremendous leap over its predecessor, the 450 MHz Power 3 processor." You can find the IBM Power 4 architecture on the right. This was a completely new architecture that had never been done before. However, during the development of Power 4, IBM faced a lot of problems. IBM was ranked 5th out of 5 companies in the Unix server segment. The key question posed to them was, could the IBM team deliver such lofty goals on time? The second critical question was that the people in the team were from different places. People were from Canada, people were from Texas, Austin, California, and several other places. All of them needed to work under one roof in unison. There was a trade-off between risk and caution. Should they take risks or should they proceed with caution? Also, in the team, there were high risk takers and seasoned realists. This led to friction in the team. However, this creative friction paid off after 4 years when they launched the Power 4. This is the photo of IBM Power 4 chip taken from IBM Power 4 website. This led to IBM's rise to power. Follow-on versions, IBM Power 5, Power 6, Power 7 became the heart of IBM's current line of industry-leading IBM Power Systems and Power Systems Express computers used by large and mid-sized companies alike. Watson, the natural language speaking computer which appeared as a contestant on the American television quiz show Jeopardy, was built on Power 7 technology. During 4 years of intense effort, the team decided to combine two processors on a single chip. It had never been done before, but if it worked, it would solve their design demands for more power and more speed and establish performance benchmarks far in advance of known competition. In 2001, IBM introduced the world's first multicore processor, a VLSI chip with two 64-bit microprocessors comprising more than 170 million transistors. This breakthrough design in architecture and semiconductor engineering allowed these two processors to work together at a very high bandwidth with large on-chip memories and with high speed buses and input-output channels. This is the generic diagram of any multi-core processor which is seen in the market today. IBM created the race for multi-core processors. This led to various events happening. The timeline of various important events in the multi-core processing industry is shown here. Starting off, in the year 2001, IBM introduced the Power 4 series multi-core processor. It was the first multi-core processor geared towards workstation and server use. Key thing to note here is that the IBM Power 4 was not introduced for the general public. In 2005, Intel and AMD released their own multi-core processors directly oriented towards the consumers. In the year 2006, Intel introduced the Core 2 processor, which is known even today for its speed, efficiency, and accuracy. In the year 2007, AMD introduced the Phenom X2 and Phenom X4 duo-core and quad-core processors into the market. In the year 2010, Intel introduced its first 6-core processor, the i7 series. In the year 2011, AMD introduced the world's first 8-core processor, the AMD FX 8150. In the year 2015, AMD introduced the first processor based on Zen architecture. In the year 2019, AMD releases the third generation of Ryzen processors, which had up to 16 cores. In the year 2020, Intel releases the first processor based on Ice Lake microarchitecture, which had up to 6 cores. This is the photo of a AMD Ryzen processor. This is the photo of a Intel Core i9 processor, which is used on most laptops and desktops today. Speed up. How was theoretical speed up measured in the first place? It was measured using Amdahl's law. In 1967, Jean Amdahl presented a paper in American Federation of Information Processing Societies (AFI-PS) on predicting theoretical speed up when using multiple processors. Amdahl's law can be formulated in the following way. N is the number of cores. P is the fraction of parallel tasks of the total number of possible tasks. Or more formally, P is the proportion of execution time that the part benefiting from improved resources originally occupied. Then the speed up S is given by S is equal to 1 by 1 minus P plus P by N. Now, as evident, the speed up increases as the number of cores increase. Suppose all tasks could be performed in parallel, that is P is equal to 1. 1 minus P goes to 0 and P goes to 1, so the speed up is simply N. That means the speed up would go linearly as the number of cores. However, this is not realizable in practice as there are certain tasks that cannot be performed in parallel. As seen from the graph on the right side, as the fraction of parallel tasks increase, the speed up also increase. The green line with 95% parallel portion has the maximum speed up over a 50% parallel portion processor. This is Amdahl's law. Moving forward, how was the idea of Power 4 first conceived? The IBM Power 4 microprocessor was developed by a team of engineers and scientists at IBM led by Dr. Bijan Dawari. Dr. Dawari was the Vice President of Technology and Emerging Products at IBM's Microelectronics Division and led the design and development of the Power 4 processor. He has been widely recognized for his contribution to the field of microprocessor design and has received numerous awards and honors throughout his career. The IBM Power 4 processor has been described as Dr. Dawari's brainchild due to his relentless pursuits to contribute to the semiconductor industry on a large scale. You can find the photo of Dr. Bijan Dawari on the right. Though it was IBM that first started the multi-core processing race, it was Intel and AMD which soon rose to power. In 2005, Intel released its first consumer-focused dual-core processor, which was a multi-core design, and later in the same year, AMD released their version with the Athlon X2 architecture. The Intel Core 2 processor line was introduced on 27 July 2006, comprising the Duo, and in 2007, the Quad and Solo sub-brands. Likewise, AMD started with the Athlon 64X2 in May 2005, which was a dual-core design, and later the Phenom series, which included the Tri and Quad cores. These days, both companies ship multi-core CPU series. The Intel 11 Gen core series maxed out 10 cores and 20 threads, while the newer 12th generation series goes up to 24 threads with a hybrid design that packs 8 performance cores that support multi-threading plus 8 efficient cores that don't. Meanwhile, AMD has its Zen 3 powerhouse with a whopping 16 cores and 32 threads. In addition to the core counts, both companies have increased cache sizes, cache levels, as well as added new ISA extensions and architecture optimizations. This struggle for total desktop domination has resulted in a couple of hits and misses for both companies alike. You can find the Intel dual core processor Core 2 Duo on the left side. This is the picture of Athlon X2 processor by AMD. Moving forward, it was mainly Intel that dominated the multi-core processing market. Intel's success in multi-core processors can be attributed to a combination of strong research and development, advanced manufacturing capabilities, strategic partnerships, brand recognition, aggressive marketing strategies, and large market share. The following factors helped Intel become a superpower in the multi-core processor industry. Intel has a strong commitment to research and development, with a significant portion of their budget dedicated to developing new technologies and improving existing ones. Intel has advanced manufacturing capabilities that allow them to produce processors with high yields and low defects. This has given them a competitive edge in terms of cost and efficiency. Intel has established strong partnerships with computer manufacturers such as Dell, HP, Lenovo, which have helped them to maintain a dominant position in the market. Brand recognition over the past 2 decades in the processor industry. Intel has been known to employ aggressive marketing strategies such as offering incentives to computer manufacturers to use their processors exclusively. The large market share of Intel helped Intel take over the multi-core processor industry from IBM during the initial days of the multi-core processor industry. On the right side, you can find 2 processor chips, the first being Intel Core 2 Duo and the second being AMD 64 Athlon X2 chip. Next, Intel's first multi-core processor was the Intel Pentium D processor. It was introduced in 2005. It was based on the NetBurst microarchitecture. It consisted of 2 Prescott CPU cores, each with 1 MB L2 cache. The main drawback of this processor was that it consumed a lot of power and its performance was not up to the mark. Thus, it was criticized by the general public for its high power consumption and mediocre performance. You can find the photo of Intel Pentium D on the right. This is the architecture used by Intel Pentium D. It is the diagram of a NetBurst D microarchitecture used by Intel Pentium D. What are the applications of multi-core processors? The first application of multi-core processors is in general purpose computing. Almost every laptop or desktop today is made of multi-core processors. Almost all Windows laptop or desktop have Intel Core processors in them. The second main use of multi-core processors is in the embedded system industry. As you can see here in the photo in the middle, there are several chips. This is the photo of an embedded system making use of several processors, and thus is the use of a multi-core processor. Network processors too make use of multi-core processors. The last diagram on the right is a network processor. Digital signal processing and graphics too make use of multi-core processors. Supercomputers are also computers that make use of multi-core processors. You can find the photo of supercomputer on the left. The core count in some supercomputers exceeds 10 million. What are the future prospects? According to a comprehensive research report, it has been found that the microprocessor industry is on a decline. After 2 decades of performance gain, we have almost reached saturation in terms of multi-core processors. Multi-core processors are not useful in terms of their capability towards massive AI or ML models such as natural language processing, image processing, recommender systems, or computer vision. We need a new architecture better suited to current and future artificial intelligence and machine learning applications, and we need it now. AI is steadily but surely eating software. ML applications are developed to achieve outcomes that are probabilistic rather than deterministic. They do not need the nth degree of high precision. They need high enough probability certainty to determine that the image of a car is indeed a car. The reduced need for precision means far more of a chip's transistors can be used for the important work of computation rather than keeping multiple cores in sync. Also, with AI/ML, there is no generic computer architecture. Each big company is coming up with its own chip. For example, Google and Amazon are designing their own chip according to their workload and with a vision to rule the modern market. With the booming of AI and ML in the recent past, the multicore industry is expected to take a serious hit. Chiplets. Chiplets are modular chips designed to form a complete system on chip. Multiple chiplets combine together to make a complex yet simple integrated circuits. Chiplets are considered to be a substitute for the multi-core processor in the modern world. On the right, you can find chiplets in golden or yellow color. These are chiplets on a package. GPUs. GPU stands for Graphic Processing Unit. GPUs have emerged as the dominant parallel architecture available to the masses. GPUs are characterized by numerous, simple yet energy efficient computational cores, thousands of simultaneously active fine grained threads, and large off chip memory bandwidth. GPUs are tailored to optimize graphics related tasks. GPU packages often contain multiple GPU cores similar in principle to a multi-core processor. You can find the photo of a GPU on the right. Modern GPUs, they use at least a billion transistors per chip. These are two examples of GPU chips having 2.6 trillion transistors and 54.2 billion transistors respectively. This concludes my seminar. Thank you.